Thermoelectric effect presented by myself Srinivas S. HOD Department of Physics JFGC Chikbalapur. In this session, already you seen last class, thermoelectric effect is the direct conversion of temperature differences to electric voltage or vice versa, or the direction of heat flow can be changing polarity of the voltage source. Seebeck effect already you seen in last video. The electricity known in physics as the Seebeck thermoelectricity, so-called Seebeck effect. Thomas Johann Seebeck found that a circuit made from two dissimilar metals with junctions at different temperatures would deflect a compass magnet or galvanometer or voltmeter or current meter you seen in last video. He discovered a small current flow and so demonstrated that heat could be converted into electricity. So just observe the diagram. So cold junction and hot junction of a copper and bismuth. So when heat is a flow from hot junction to cold junction, there is a set of a EMF. The EMF can be measured by using the magnetic needle. Seebeck effect from the diagram. A heat is a flow from hot junction to cold junction. A voltage is shown in a voltmeter. That voltage is directly proportional to temperature differences across the cold and hot junction, that is delta T. Therefore, V is the voltage is directly proportional to delta T, or remove the direct proportionality, we'll get a alpha. Alpha is nothing but Seebeck coefficient. Therefore, alpha equals to VAB divided by delta T. Relation between EMF and temperature. So the open voltage of thermocouple is given by the E equals to A theta plus B theta square. A and B are the coefficients of a Seebeck. Theta is the temperature at a junctions. Now differentiate the above equation. We'll get a dE by d theta. That is nothing but P. P is nothing but thermoelectric power. So now differentiate the above equation, EMF expression. We get P equals to A plus of 2 times of B into theta. Now plot a graph. Thermoelectric EMF versus temperature. We'll get a parabola curve. As increasing the temperature, EMF will be gradually increases. When we reach at a particular temperature, the EMF showed a maximum. Again, we increase the temperature, the EMF is gradually decreases. Where EMF is a maximum, such a temperature is a neutral temperature. It is denoted by Tn. So where the curve will be reverse, takes place reverse, that is nothing but inversion temperature. It is denoted by T high. So variation of thermoelectric EMF with temperature. So Tn is a neutral temperature, constant for a given thermocouple. Ti is inversion temperature, behind which EMF start increases in opposite direction. So now see here. So here Tn is nothing but neutral temperature. What is a neutral temperature? It is a temperature at which thermo EMF is maximum. So Ti is nothing but inversion temperature. What is inversion temperature? Inversion temperature is a temperature of the cold junction at which the thermo EMF curve will be reverse. So now see of here. So here 0 degree centigrade we denoted by T naught in Kelvin scale. So at maximum Tn and this is a Ti. So this is can be written as T high inversion temperature minus of Tn equals to Tn neutral temperature minus of initial means at origin temperature T0. So this is nothing but equation. What is the inversion temperature? it is denoted by Ti. The particular inversion temperature is a particular temperature of the junctions at which the thermo EMF becomes zero, is called the inversion temperature. On heating slightly further, the direction of the thermo EMF is reverse, as the number densities of both the metals used are reversed. Therefore, the current reverses direction. This temperature depends on the temperature of the cold junction and nature of the material. So in the graph showed here, T high is nothing but inversion temperature. So here EMF is almost 0. Next, neutral temperature. It is the temperature of the hot junction of a thermocouple at which the electromotive force of the thermocouple attains its maximum value when the cold junction is maintained at a constant temperature of 0 degree centigrade. The graph showed here. So at a neutral temperature, the EMF will be maximum. So this is the definitions of a neutral temperature and inversion temperature. So these things are very important in the view of the examination point also. And next we see the what is the Peltier effect. In what is the Peltier effect? In Peltier effect. In 1834, French scientist Peltier discovered the Peltier effect. According to him, when electric current is passed through a circuit consisting of two dissimilar metals, heat is evolved at one junction and absorbed at the other junction. This is called Peltier effect. Peltier effect is the converse of Seebeck effect. So now see the circuit diagram. The circuit diagram consists of a dissimilar thermocouple of copper and iron and battery. So at the junction 1, the current flow from copper to iron, there is heat absorbed. At junction 2, the current is flow from iron to copper, there is heat liberated. So now changes the polarity of a battery. So now observe here at junction 2, the heat is absorbed. At junction 1, heat is liberated. There is a takes place a reverse process. This is the Peltier effect. Peltier coefficient, it is denoted by pi. So it is defined as the amount of heat energy absorbed or evolved at one of the junctions of a thermocouple when 1 ampere current flows per 1 second or 1 coulomb is called Peltier coefficient. It is denoted by pi. Its unit is volt. If capital H is the quantity of heat absorbed or evolved at one junction, then its expression is given by capital H equals to pi times of current into time. So H is the amount of heat energy absorbed or liberated. So now see the diagram. So at a junction copper and iron, the heat is liberated. At the junction 1, the heat is absorbed.